Hello. Today we're going to discuss Chapter 2, which begins with modeling via systems of equations. But before we do so, let's review some properties from last time about integrating factors for linear differential equations. Here's the idea. Say that we have a homogeneous equation, that is, dy dt equals a of t times y. We know that we can multiply both sides by dt and by 1 over y, and then integrate in order to find our solution y of t. As motivation, say that we have a non-homogeneous equation, dy dt equals a of t times y plus b of t. We'll try to solve this equation by using a similar technique. First, let's bring all of the y's to one side by subtracting a of t times y, and then we'll multiply by a general function mu of t. What if the left-hand side were the derivative of something? That is, what if the left-hand side, mu times dy dt, minus a of t times mu of t times y, equals the derivative of a product, mu of t times y. Using the product rule, we then see that we'd like to set mu prime of t equal to negative a of t times mu. The following proposition explains how to solve this equation and why this helps. First, the solution to mu prime of t equals negative a of t times mu is the exponential of negative the integral a of t dt. Using this, a particular solution to the non-homogeneous equation dy dt equals a of t times y plus b of t is the following function. Y sub p of t, a particular solution, is given by 1 over mu of t times the integral mu of tau b of tau d tau. Let's put all of this together into an algorithm to explain how to solve a non-homogeneous equation dy dt equals a of t times y plus b of t. First, we'll compute the integrating factor as mu of t is the exponential of negative the integral a of t dt. Second, we'll compute the integral u of t as the integral of mu of t b of t dt. Finally, we'll return the function a constant c divided by mu of t plus the ratio u of t divided by mu of t. Now let's discuss some properties of modeling via systems of equations. In order to get some intuition behind why we'd like to do this, I'd like to start with a story and begin with Pierre-François Verhoest. He is a Belgian mathematician who was interested in modeling populations. In 1845, he gave the following expression for how a population should grow. He stated that the rate of change of the size of a population is proportional to the size of the population as well as the distance the population is from its carrying capacity. In other words, if we let P of t denote the size of the population at time t, then its change, dp dt, should be proportional to 1 minus P over n here's the carrying capacity, times P itself. Putting this together, Verhoest called this the logistic growth model, although some people simply call this the Verhoest model. Simply put, if we let k be our constant of proportionality, then we have the differential equation dp dt equals k times 1 minus p over n times p. We've already seen that we know how to solve such an equation. Since this is a separable equation, we can work things out to see that p of t should be n divided by 1 plus an exponential. Here, we've let this constant t, I, and f be the inflection point for time. This is the point in time in which the rate of change for our population is actually slowing. That is, dp dt is always positive, but now we'll want to look at the second derivative. So before the inflection point, the second derivative is positive. That is that the rate of change is increasing, whereas when we're beyond the inflection point, then the second derivative is negative. That is, our rate of change is decreasing. There were two American mathematicians who were very interested in this idea of the Verhoest model. Raymond Pearl is an American biologist, and Lowell J. Reed was an American statistician. They were very interested in looking at the population growth of the United States. We discussed this the very first day in class, but we'll revisit it today for a little bit. They were interested in the population from 1790 up through 1920. In fact, they wrote a paper in 1920 stating that the population of the United States from 1790 through 1910 can be fit using the logistic growth model. And in fact, in their paper, they did write out some of the numbers that you see here on your screen. Notice that they thought that the inflection point is 1914, which meant, since they wrote the paper in 1920, they thought that the rate of change of growth for the United States was slowing down. In fact, they really went on to say that the US population would not grow much beyond about 197 million people. They do spend some time there in the article discussing what would it look like if the United States had a population of 197 million people. Unfortunately, their model isn't exactly right. Indeed, in 1970, the US population reached 203 million people. Using this, back during the very first day of this class, we used the data from 1790 all the way through 2010 to get a slightly better fit of the US Census data. Again, you can see some of the numbers here on your screen. Notice that we determined that the inflection point for the population won't be for another 50 years, about 2076 or so. In fact, these new numbers predict that the US population will grow to be about 1.12 billion people, billion with the B. So we'll use this now as the motivating question. We've seen that the logistic growth model predicts the size of a population, but what if there are two competing populations, not just one? Well, this leads us into what we're going to discuss in some detail today, what's called the predator-prey model. Indeed, let's say that we have two populations, one that we'll call predators and the other that we'll call prey. Let's give some examples. We might be interested in, let's say, the brown bear fishing for salmon. The brown bear will be the predators and the salmon will be the prey. Or we're interested in how foxes maybe hunt for rabbits. In this case, the foxes will be the predators and the rabbits will be the prey. Or perhaps we're interested in how lions hunt zebra. The lions will form the predators and the zebra will form the prey. Or we're interested in, well, predators versus alien. I think you get a better idea of where this is going now. There were two mathematicians who were very interested in all of this. There's an American biophysicist named Alfred Latka, who in 1910 was actually interested in looking at modeling autocatalytic chemical reactions. And using some of his ideas, he came up with a system of equations. About 15 years later, in 1926, the Italian physicist Vittorio Volterra focused on the number of fish caught in the Adriatic Sea, and again, he came up with a similar set of equations. We're going to discuss these equations in some more detail today. To get an idea of what this means, let's set up some notation. Let's let f of t denote the size of the population of predators at time t, and r of t denote the size of the population of the prey at time t. Here, you can think of f as standing for fox, whereas r will stand for rabbit. In order to model these two populations, let's make some assumptions for a so-called predator-prey model. First, as with exponential growth, we're going to assume that the rate of change of each population is proportional to its size. Indeed, in order for the population of rabbits to grow, we need more rabbits in order to procreate. Second, there should exist a number n sub f, such that if the size of the number of predators is large enough, then the prey are hunted and then their population decreases. However, if the number of predators is small enough, then the predators cannot effectively hunt the prey, and the size of the prey population will increase. So there should be some number n sub f that tells us if the number of predators is either too large or too small, then the size of the population of the prey will either decrease or increase. Similarly, there should exist a number n sub r, such that if the size of the number of prey is large enough, then the prey are numerous, and the population of predators will increase. However, if the size of the prey is small enough, then the prey will be hard to find, and the population of the predators will decrease. Let's put this together by using proportionality. You can see here that now we're saying that the rate of change for the rabbits, that is for the prey, should be proportional to 1 minus f over n sub f. Remember the f here tells us the number of predators, that is the foxes, times r, the number of rabbits. What this means is that in order for us to have an increase in the population of rabbits, we must have some rabbits so that they can procreate. That is, dr dt should be proportional to something times r. Similarly, in order for the size of the population of foxes to increase, that is for our predators, we must at least have some foxes there in order to procreate. So df dt similarly should also be proportional to r. Now let's take a look at these factors 1 minus f over n sub f. If f is greater than n sub f, that is, if the number of foxes is very large, the foxes will hunt the rabbits, and then we expect dr dt to be negative. So if f is greater than this number n sub f, then we expect dr dt to be less than 0. Similarly, let's take a look at the factor r over n sub r minus 1. If the number of rabbits r is large enough, then it'll be easier for the foxes to hunt them, and then we expect that the size of the population of the foxes will increase. Putting all of this together, we can now say that we have a constant of proportionality alpha for the rabbits, and we have a constant of proportionality gamma for the foxes. This means that we have a system of two equations, two unknowns. Dr dt equals alpha times r minus beta times r times f, and df dt equals negative gamma times f plus delta times r times f. You'll see here that we can express n sub r as gamma over delta and n sub f as alpha over beta. These two equations are typically what are called the Latka-Volterra predator-prey model. On your screen, you'll see an example of a solution that is a plot of the rabbit's R and a plot of the fox's F. As the course progresses, we're going to discuss exactly what do these graphs mean, how we can numerically find these, and if there's a better way in which we can really analytically and qualitatively understand the solutions. But for now, let's ask the following question. Is this the most general model that we could possibly write down? Well, let's perform a little thought experiment here just to see, does this really make sense? Let's consider the predator-prey model where we're going to assume n sub r goes to infinity and n sub f also goes to infinity. Remember that n sub r is this boundary point that tells us that if the number of rabbits is larger than this, then the number of foxes will increase. Whereas if the number of rabbits is less than this, then the number of foxes will decrease. This is the same thing in our equations as setting delta to 0 and beta to 0, which means that we have two first-order differential equations. Dr dt equals alpha times r, and df dt equals negative gamma times f. These equations we know how to solve. They correspond to exponential growth and exponential decay, respectively. Let's see what this really means. This now says that the number of prey can grow without bound. That is, the number of rabbits, r of t, will tend to infinity as time increases without bound. This makes sense because here we're assuming that our factors n sub r really can be whatever we want. We're letting n sub r grow, which means that the number of rabbits should also grow. However, this also says that the regions in which the rabbits and foxes live is so large that the predators cannot find them. This is the idea of n sub f. N sub f tending to infinity means that if we have foxes, unfortunately there aren't enough foxes to keep the rabbit population in check. So actually the number of foxes will decrease and go to 0. F of t tends to 0 as t tends to infinity. And we really have to ask the question, does this really make sense? Because we know that we just can't have an arbitrary number of rabbits, that really the number of rabbits has to be kept in check based on the amount of space that we have and also based on the amount of food that there is. So here's our motivating question. To find the situation above, we assumed that we have an exponential growth model. So what if instead we assume that we have a logistic growth model? Let's do the following. Let's assume that there is a carrying capacity capital N for the prey for the rabbits. This means that we have a model where we're going to weight the predator-prey model along with the logistic growth model. Now here, we know that from the predator-prey model, we have a factor of 1 minus F over N sub F times R. And for the logistic growth model, we have a factor of 1 minus R over N times R. So let's say that we have two real numbers between 0 and 1, which we'll write as 1 minus n sub r over n and n sub r over n. These are two positive real numbers that sum to 1, and now we'll have a weighted average of the predator-prey model and our logistic growth model. We're only doing this for the prey, for the rabbits. We're not doing this for the foxes. Once we play around with the algebra a little bit, we find that we can express this so-called modified predator-prey model in a slightly simpler form. We can write this as dr dt equals a constant of proportionality alpha times 1 minus r over n times r. Again, remember that n here is the carrying capacity for the rabbits, minus beta times r times f. For the number of foxes, we have df dt equals negative gamma times f plus delta times r times f. As before, we can try to express the n sub r and n sub f in terms of alpha, beta, gamma, and delta. This new set of equations is what's called the logistic predator-prey model. In coming lessons, we'll discuss a little bit more about the system, how to find the solutions, and even some analytic and qualitative properties we can discuss. Thanks very much for watching.